you know, thermodynamically, when we talked about stress, we defined it as the tensor gradient of some strain energy density functional with respect to the components of the strain tensor. And by the way, anytime that I don't sort of explicitly, you know, a lot of times I write stress strain, and we know that for finite deformations there's lots of different stress and strain measures. Anytime I don't specifically say something about that, we're just talking about Cauchy stress and the small strain tensor, okay? So, you know, we made this sort of thermodynamic argument for what the stress tensor is. And the strain energy density functional, we said, is some function of like the density times the Helmholtz free energy. And we sort of heuristically made the arguments that we can then say that there's the Helmholtz free energy is some function of the strain components. And we also had, if I didn't say specifically, but we also had temperature there, okay? And so if we look at one of these plastic stress strain curves, so if I'm saying that the stress is a function of the strain and the temperature, what?
Are those, I'm talking about the experiments.
Mm-hmm.
Are those stress strain experiments repeatable for geometry?
Yeah. Yeah, they're you know, I mean, concrete is by no means a homogeneous material, right? Every sample you test is going to have different placements of aggregates and other things. But if your representative sample size is large enough, then you will get sort of an average response. Now, you know, the curves won't be perfectly right on top of one another, but within, you know, you can definitely draw statistical, you know, if you do enough experiments, you can have a meaningful mean, and you know, the standard deviations aren't, you know, 50% of the value. You know, there'll be, you know, relatively small spread. So the trick there is to have large enough sample sizes, right? Now something like a shale or something, you know, if you exclude like natural fractures and all that stuff, I mean, if you get a really nice core, you could probably get away with much smaller samples. So a representative sample size for concrete has to be about maybe 3 inches in diameter. So it's a fairly big sample, right? But for shales, you could probably get by with, you know, 1.5 inch samples. And, you know, if you do enough tests, you'll see that they're fairly repeatable. So let's, you know, so basically what I'm saying here is that the stress, according to this definition, this sort of hyperelasticity. So hyperelasticity means that the stress derives from some strain energy density function. Okay? So if the strain energy density function is just a function of the components of the strain tensor and temperature, if I give you those things, right? If I give you the components of the strain tensor and I give you the temperature, and we know the strain energy density functional, you should be able to tell me what the stress is. Okay? But let's look at one of these cases for plasticity again. So here's my stress strain curve. And let's say this is just one dimensional, okay? So my strain tensor is just, it just has one entry right up here, sigma 1, 1. Right? Everything else is 0. Let's say that I give you, I say sigma 1, 1 is equal to sigma 0. And I ask you what the stress is. What's the stress? Right? This is stress on this axis, so I should just be able to draw a line up and read it off, right? Uh-oh, there's 2 values. Right? There's 2 values. So apparently I don't have enough information in just the strain and temperature. Right? In this case, we can even assume isothermal, so temperature doesn't even matter. There's not enough information if I just give you the strain tensor for you to tell me what the stress is. You have to have some other information notably the history of loading, right? You need to know where you're at in the history of loading, in this case, for me to tell you what the stress is, okay? So you actually, in this case, you need some other variable, right? So the stress is apparently, in case of plasticity, the stress is not just a function of the strain and temperature, but some other thing that we'll call an internal state variable, okay? So this internal state variable can include information about the history of loading. So let's have a conversation about internal state variables. So this is the symbol Xc, and I put a vector symbol over the top of it to indicate that even though I'm just writing one thing, it could be just like the components of the stress tensor have 9 components. I mean, this vector could have 100 components to it, right? So it could, in fact, be 100 individual internal state variables that describe the history of loading or describe whatever extra information I need to tell you what the state of stress is, okay? And so Xc may be a physical variable. And what sort of information or where that could come from, it could come from the microstructure. So Xc could come from the microstructure. It could sort of include information about, if we're talking about metals, the grain size. If we're talking about rocks, it could contain some information about the microstructure of the rock or any flaw or density distribution, flaw densities that occur. It could contain information or be a variable that includes some physiochemical reaction. So a lot of times, especially in rocks and geomaterials, you can have absorption, desorption. So you can actually have chemical reactions that are occurring during the deformation process or because of the deformation process, and sort of actually physically changes the material of the rock. You could also have, if you're talking about metals or something like that, you could have phase changes. So these internal state variables could characterize the phase change of the material. Like I said before, I sort of mentioned this when I said structure. I guess since I'm going to list this separately, let's confine structure to the actual microstructure itself, maybe grain size or aggregate size in some rock or characteristic material. Here, I guess, since I'm going to lay it out explicitly, densities of structural defects. And so you can actually have internal state variables. This is actually a hot area in mechanics research, and it's so-called micromechanics. So a lot of times what you do in micromechanics is you assume some distribution of structural defects, and then you either phenomenologically or physically develop a law for how those defects will evolve with time. And then you can use those. So how those will evolve with time give you your history variable, and it gives you some information that you can use to construct or determine what those internal state variables are and how they affect the continuum or macro motion. But more often than not, these internal state variables are phenomenological. So what I mean by phenomenological is a lot of times it can be difficult to, especially if you think about, well, since I haven't really told you what plastic strain is yet, but we notably use one variable a lot when we do plasticity modeling. It's called a plastic strain or equivalent plastic strain. And it's sort of one state variable that is all-encompassing in the sense that it governs or includes the effects of all of the small-scale things that could happen in plasticity. So if you're talking about a metal that's plastically deforming, like our paperclip, I mean, the physical mechanism there is that you actually have slip on crystallographic planes, okay, that's occurring. Now, we don't, at the continuum level, if we're modeling an airplane, we don't go in and we don't model every single slip plane to determine, how every crystal is going to reorient or remain permanently deformed. If we did that, we could never solve a problem on the scale of the airplane, right? And so we use these internal state variables, and namely one called equivalent plastic strain. As sort of an all-encompassing measure of all of the microstructural information that, or all the microstructural plastic deformation that's occurring. And we say it's phenomenological because, again, we don't derive that from any kind of first principle. We use it as a placeholder, but at the same time, it's phenomenological in the sense that we do get these constitutive models from an experiment, right? So the plastic strain or the flow rule, the evolution of the plastic strain, we define as something that represents an experiment really well, okay? And so it's not first principles in the sense that we're actually solving F equals MA on every crystal, right? We have this one variable that encompasses all the information. But it turns out that it models experiments very, very well. And so by far today, while there are certainly people that do crystal plasticity and all kind of other all the way down to molecular scale modeling of plasticity, by far in an engineering sense, this notion of an equivalent plastic strain, this special internal state variable that kind of governs all things plastic flow is the way we do it. And that includes in rocks. Now, we're going to start talking about plasticity models a little bit, and we'll start with metals because it's simple. But of course, we want to get to rocks, geomechanics. So the thing that makes metals simple is we assume that when a metal's deformed plastically, their deformation is isochoric. So it's without volume change, which means that the pressure or the dilatation response of the material doesn't affect the plasticity. It's only the shear deformation, okay? And then, so that's sort of the first step, and then we'll go on to talk about rocks. Now, rocks actually have a pressure dependence as well, and so we'll add in that complexity too, okay? So one of the assumptions that we make is that the total strain tensor can be decomposed into an elastic part and a plastic part. And whenever you see it written like this additive decomposition of the strain, this is really only true for small strains. So again, our definition of small strain is when the displacement gradients are much, much less than 1. Okay. So more correctly, which will hold for large deformations too, is that we use an additive decomposition of the strain rates. So that we say the total strain rate can be additively decomposed into an elastic and a plastic part. So the elastic part, we know, right? That's Hooke's law. And so we just have to come up with a way to define the plastic part of the strain. And so, what we'll end up doing is we'll sort of rearrange this equation so that we say that, the elastic strain is equal to the total strain minus the plastic strain. So the total strain we know, we just, we always do these computationally, right? So we take a step in the simulation, solve for the displacements, we can compute the total strain, right? And then if we have some rule, some flow rule that governs the plastic strain, and this is where our phenomenological model comes in, or our equivalent plastic strain comes in, which governs how the evolution of the plastic strain tensor flows, then we can compute the elastic strain, right? And then if we know the elastic strain, we can plug it back into a hyperelastic or Hooke's law type constitutive model to update the stress. Okay? That's sort of how we're going to do this.